Hey y'all, we're on page 24 and this is Sinusoidal Functions Day 3. So we're going to do number 1, it's a problem about a tsunami. We're actually going to ignore number 2 for now, so you can actually just go ahead and cross that out. Go ahead and back to number 1, go ahead and pause the video, read that so you know what we're talking about. I'm going to jump right in. We're talking about the tsunami and we have a bunch of water levels that we have to deal with, and so just kind of keep that in mind because we have water level that will be at normal level, and then water level will rise and it will fall, okay? And then it tells you some information that's very, very direct and to the point. The first thing it tells you is that the period is 15 minutes, so that's the time it takes to, for example, reach a high tide and come back to a high tide. And it tells you that the amplitude of the tsunami is 10 meters. So again, that's very direct for your graph. Very, very easy to put on there. And then lastly, it tells you that the normal depth of the water is 9 meters. The normal depth of the water is 9 meters. So let's go ahead and graph what we can. So I know, because we're talking about a tsunami, we are dealing with depth of water, which is going to be your y value. And the depth of water is in meters. And on the x-axis will be your time, and this time is, in this case, in minutes. Alright, so now let's find what we can actually put on there. So period, I can't really plot on there. That tells me where my second or third points will be, but I need to find my first point. So let's keep looking. Amplitude, again, won't help me right now. It will in a minute or two when we actually have a first point. But if I keep reading, it tells me that the normal depth of the water is 9 meters. Okay, so that's something I can deal with. I can work with right now. Normal depth is going to be at 9 meters, so 9 would, let's say, is about here. So 9 is actually going to represent, because it's your normal depth, it's going to represent the, what we call the center line in our graphs. So 9 will represent the normal depth, the center line, the mid. Okay, so now knowing that, we have to actually think about this and find a first point, because that's all the information that's given to us. Now, if you think about the time starts ticking after the tsunami actually starts, after it actually hits. So what that means is that the high on the tsunami will be when time is 0. So in other words, the high point will be on the y-axis directly. So if I know the normal, the mid, the center line, is at 9 and I have an amplitude of 10, that means my highest point will be at 19. There you go. And like we said, it's on the y-axis, so there's your first point. Now I can go back and use the period, because if I know the period is 15 minutes, that means it's going to take 15 minutes, so let's say here's about 15 minutes, to get back to that same high point, which is at 19 meters. So there you go. And if you were to continue, if you're curious, at 30 minutes, another 15 minutes away, you'll have another high point. Okay? So now let's go back and figure out some more stuff, because if you know two high points are at 0 and 15, then right in the middle at 7.5 minutes should be a low point. Now, before we just kind of put it anywhere, we have to actually find a low point on the y-axis. So if I go back, I know my midpoint, my center line is at 9, I know my amplitude is 10, which means 10 meters below the center line. So in other words, at -1 should be my low point. So 7.5 comma -1 is where my low point should be. And so if I have my high points and I have my low points, and I know my midpoints should be directly, in this case, on my center line, just like that. Okay, so there we go. We have one period on the graph, and if you were to continue, you know, it would follow just like that, and so on. So there's my sinusoidal graph. Now I need to find the transformations A, B, C, and D in order to write my equation, cos of And instead of theta, I'm going to use the letter T to represent time. Okay, so now let's fill in everything. Now remember, some of the things that were given are very direct. For example, A, the amplitude, is given to you exactly as 10. That's easy. Remember, that goes right in front of cos. B value, you're going to have to put a little bit of work in. Luckily, the period is given. Now, you could, if you didn't realize or if you didn't remember that, you could always go back and count the number of minutes that it takes. But it is right there, so we'll just go ahead and use it. And remember, to find B, knowing the period, you can always use this formula. Period equals 2 pi over B. Let me plug in the period, which is 15 minutes. Set it equal to 2 pi over B so I can solve for B. So I'm going to put 15 over 1 so that I can cross multiply to give me 15B equals 2 pi. And I'm going to divide by 15. And so B equals 2 pi over 15. Now that does not simplify, so I'm going to actually leave it just like that. 2 pi over 15. And remember, that goes right between cos and your angle, in this case, t. So right over here, 2 pi over 15. Okay, C, remember, is your phase shift. Now, because this is a cosine function, I'm going to look for a high point on my graph. Luckily, if you take a look on the y-axis, you have a high point directly on there. So what that means is because you have a high point on the y-axis, just like it is for the parent, there actually is no phase shift. Phase shift is 0, C value is 0. Okay, and then lastly, D. Now remember, D is based on the location, the exact location of your center line. So if I know my center line is at 9, then I know D is a positive 9. And that's going to go in at the very end. Okay, so there's my equation. And I'm going to go ahead and plug that into the calculator in just a minute because what I'm asked for next is in part A, it says predict the depth of the water. In other words, if you take a look at your graph, the depth of water is represented by your y's. So I'm going to say, it says predict the depth, so I'm going to say what is y when the following times are given. So when x or t is given. And you have 3 separate ones that you'll have to find. So let's actually go ahead and plug this into the calculator first. So I'm going to go to my tab and I'm going to type in 10 cos of 2 pi over 15. And let me see here. Let me put in an extra set of parentheses so I can cover myself. And plus 9 at the end. And so if I hit enter, uh-oh, what happened? Plus 9. Okay, so there we go, that's better. Okay, so now if I zoom out, because as you can see, it's a little bit off. It's a little bit off. I can't really see it very well. So I'm going to go to Window Zoom, and I'm just going to zoom out a little bit. Okay, and that's about right. So I can see a little bit more than the graph. So now I want to find, remember, I want to find y, what is y, when x is given. So remember, that's actually the easiest thing to find. So I'm going to go to Menu and Trace, Graph Trace, and type in the exact x value that you're looking for. The first one is 2, so I'm going to type in 2, enter, and it gives me a y value of 15.7, don't forget meters. Okay, the next one, so again, go to Menu, down to Trace, Graph Trace, and the next one is 4 minutes, so 4, enter, and so you'll have 7.95 meters. And number 3, so again, menu, go down to trace, graph trace, 12, enter, and that gives you 12.1 meters. So there's your depth of water when those are the exact times. Part B says, according to your model, so according to what we graphed and according to what we have here, the equation, what will be the minimum depth of the water? What will be the minimum depth? So the minimum depth of the water is actually at 0 meters in this case. That's the lowest the water will ever go. It doesn't make sense to go below 0. All right. Part C says between what two times is there no water at the pier? So what that means is we're talking about 2 times, so T equals what when there is no water. So in other words, when Y equals 0, when there is no water. So let's go into our graph, and we're going to have to say that, okay, now that I know that Y equals 0, what's my time? What's my X? So I'm going to hit tab so it shows me another spot to type in. And because I know Y equals 0, here's 0, enter. And it creates a line for me there on Y equals 0. And because I'm looking for times, I'm looking for X values where Y is 0. In other words, I want intersections right there. So I'm going to go down, let me see if I can zoom in just a little bit, right in here. Okay, that's good. So I want these 2 intersections right over here, because those are my first 2 times. These would be my second 2 times. I don't want those. I'm not going to look at the negatives because it doesn't make sense to have negative time. So I'm going to go to menu, go down to analyze graph. I want the intersections. So on the left side of that first one for the lower bound and a little bit to the right side. And my intersection, it says when Y is 0, is the first time is 6.42 minutes. And the second time will be the second intersection right next to it. So again, menu, go down to analyze, intersection. And my lower bound, I'm going to just go a little bit to the left of that intersection, and upper bound will be to the right side. And don't know how well y'all can see that on your screens, but we have 8.58 minutes. There you go. Part D says the wavelength of a wave is the distance from crest to crest in one period. If a tsunami travels at 1,200 kilometers per hour, what is the wavelength? So we're looking for wavelength, which we know is 1,200, it's given to us 1,200 kilometers per hour. So all we have to do is realize, okay, in our case, one period is 15 minutes. Well, now think about it. If we're trying to just convert that to hours, how many 15-minute intervals are there in an hour? Yeah, there are 4. So we're going to say that we have 1,200 kilometers per hour divided by 4 to give you 300 kilometers. Just kilometers. And that's going to be your wavelength. And there you go. Thanks for watching, guys. Bye.